All right, so I think we can ask Dr. Utane to start, please.
Okay, thank you very much, Ira. And so I will share my screen now, which is this one. Okay. All right, I hope you can all see the screen.
Yes.
Okay, good. And I guess the sound level is okay. So, right, okay, so let's start on, still need to arrange my screen a bit. Okay, that's it. I'm fine now. Ready to start. Okay, so yesterday we kind of look at this sort of a clustering analysis, which is a kind of unsupervised machine learning. Now we will look at kind of the other end, which is a supervised method, and of course the supervised machine learning has a a bigger list than just classification. Classification is one of which has quite a lot of applications in a lot of everyday life in research as well. So let's look at this kind of for the first talk this morning, I will try to kind of go in general in terms of classification. Some of the example algorithm might be used in order to make a certain point or to highlight the ideas. And then the second session will go into looking at some of the kind of popular or quite effective algorithm for classification machine learning. Okay, so the outline for the first part will have a quick kind of introduction a little bit. I said a little bit there between machine learning, supervised and unsupervised, and then we'll look at what we mean by classification tasks and what it takes, right, for the machine or the computer to give you this kind of classifications. Okay, apart from of course data, and then we'll look at some of the important things, crucial stuff that you would need to feed it. Things like, of course, data. There's features engineering, feature selection, which is of course very important. Then we will have a look at some of the approach, and finally, to be able to tell whether the model that we have trained or have in our hands, or the further one that you want to develop, is good enough, right? So there will be part on the model evaluation, okay, and interpretation of these, for example. Okay, so just a quick cap of the machine learning. Okay, so what does it mean to learn? Do we actually, is it just the coding? Is it just the if statement that we normally do to choose things, right? Because now we're talking about classification. So many of us who do some coding or some writing or program might have set something similar, like conditions, and then you can kind of put things into classes, right? Categories. So, but what does it mean, right? So in this case, to learn means you start off from a single set of data or certain rules, but then the machine itself gain this knowledge, right? By understanding the pattern or whatever, right? Study, or what you can call it, learning study or whatever, and can use that experience to kind of making a further prediction of further forecasting of certain values. Okay, so that is learning. It's not like what we used to the word with the learning by heart. So that's more of a memorization, right? So we're not talking about just memorization here. So if the data are on the disk, so that's what is written, you can load it up, you can then kind of like search or query. That is just memorization, and it's just kind of a way to recover data rather than actually inferring or make some induction from it. Okay, so to be able to program the machine to learn, okay, there will be certain requirement. Okay, so in terms of the machine learning, so what we say here is that you feed it with some data, and with certain rule, with certain optimization, you will see pattern again and again, things that we tend to call cost function and so on, which are being used in order to make a judgment whether you arrive at the release some optimal answer that you want to stop and things like that. Okay, or sometimes this process can be the process that you want it to be automated, right? For example, you have a video feed that you want it to be real time. You want to have some kind of picture extraction, so you can tell whether this is a person, this is just some animal walking past, and if it's a person, this is someone in your family members, and whether you need to alert some security, for example, if that's your thing, right? If your home is really you worry about your security and so on, right? That's just example. So either way, you can get some useful information, right? And you can use it for other things. So application is very, very wide, as you can imagine. Okay, and sometimes it could be kind of binary 0 or 1, and you can get some probabilistic model as well, because the computer gives you this information or learning, but you don't want the computer to make the decision straight away, right? But rather have this information presented to human to make a decision on this probabilistic likelihood that the outcome, how likely it is to be this outcome, and so on. Okay, so a lot of these, most of the time, also quite important for the area where we lack of general theory, right? So you might have a bunch of data, you try to make sense of it, you see that there's some pattern to it, but you're not quite sure what it is, and your angle, your approaching angle is not theory. So this is a way to kind of uncover that. So things like regression and things like that, right? You might need to assume certain relationship, either linear or whatever other relationship, and then that could be another way of saying that for a bunch of data point, then you can get a relationship. So that's kind of enter into this machine learning, but rather kind of classical, right? Once you get that relationship, then you would be able to predict or forecast. So if you start from certain conditions, where would you end up in that spectrum, for example? Okay, so so why do we need machine learning? Many of the tasks cannot be defined very well. Okay, only some examples of kind of like numerical argument, if you like. Okay, so like recognition of facial or people. There's no way to kind of come up with some theory, and you can like code it, implement it like a normal theory to distinguish stuff, right? But rather, actually, you have to learn from many different photos, and then people with different genders, with different race, and so on. Facial features could be very different. Okay, and in order to do that, is you know, it cannot describe it very well in terms of theory. The second case would be there's a large amount of data. There's some diversity to the data. The generation rate of the data itself is huge. Okay, so that's in the territory of what we would call big data. And so most of the time you need to kind of take in all those data, and due to its kind of wide range of conditions, you want to make sure that you take everything into account. So most often you need some of this kind of machine learning to be applied to these data with various technique. The amount of knowledge regarding certain problem may be too large, okay, for any humans or expert, for example, to kind of look through and kind of come up with some underlying theory, because it could be depending on various parameters, variables. Those different variables could be correlated among each other, so it's not a simple task to kind of look at them and try to kind of discern what sort of underlying relationship there. So it's probably the more efficient way to kind of like throw in to the machine learning and see what we get from it. The final point is again still kind of related to things that you would call big data, right? The conditions, environment can change over time or constantly. So in order to be able to kind of like, if you were to kind of code in by hands to take into account all those conditions, wouldn't be very efficient, right? We might try that with, let's say, image processing of the stellar photometry, for example. You can try to kind of model what happened when you try to extract the flux when the point spread function or the seeing is bad. Of course, that's one of the way you can try. But then, as you know, if the condition is much more kind of diverse, right? When it's stable, it's fine. You can apply it and you can get a pretty good result from it. But when it's quite condition is quite variable, then that's where your conventional approach tend to break down, and this is where machine learning can help you. So the approach is usually there's some input data there, label or unlabeled. Okay, you put through something called machine learning. That is the generic term. It could mean anything. Okay, so it's you know, certain codes and algorithm that learning and optimizing, and finally you end up with something like a model. In this case, if you're interested in classification, you could call that model a classifier, right? So once you put something, information that related, so have a similar kind of property with input data, or sometimes called instance, you put it in and see what the classifier or the model give you, right? And with that information, then you can choose to act on it however you like. And classification can be binary, it can be yes or no, 0 or 1, male or female. What else? Something along that line, right? Yes or no. Like thing, for example, you go to the bank, you ask for a loan from the bank in order to, let's say you said you want to run some business, you want some money, so the bank could, you know, run certain algorithm on you based on your informations and the data they have on the past experience or past either success or failure with the people that they give out the loan, and whether they're able to return the money and things like that, right? So finally, then that give you a prediction of classifications of categories, and then people can choose to how to act on it. But sometimes automated system, it might not even go through human at all. It's just make decision and go through it by itself. Things like, you know, AI. Okay, so machine learning would be a base where AI will need, and then but they are automated, so they can decide to act on it with certain rule, maybe, because we, as we know, we some people are afraid of that. Okay, so so machine learning can be kind of split into various area here. So of course, there's a learning task you need to do, what you want to do, what you want to predict, what you want to get out of it, the data. Okay, so these are very important components of machine learning. So what data do you have? What's the quality of it? Okay, so always the rule of thumb is that the garbage in, then you get the garbage out. So also very important to kind of make sure that the data you feed into the model or constructing the model is up to a good quality, and you know, or at least you can characterize what the missing data is and how would that kind of introduce bias into your model. Okay, and then things like representation, how well, you know, your representation that you pick, because if you pick things representation which is not suitable for your data set, it might not be a good way to kind of like get the good model anyway. So as you will see, there are many algorithms, and various different algorithms can be good for certain problems and so on. So this is kind of along that line, which is going to a similar thing with the method and estimation as well. So with these, once you train it, you get something that you can use, but more often, sometimes you need to feed some kind of modeling or hypothesis into that as well. Like, for example, yesterday we talked about clustering. There's a different way to measure distance and things like that. And so these have to be kind of chosen appropriately based on the problem that, the problem at hand that you would be interested in solving. And then, of course, once you get that, you need to perform certain evaluation, quantifiable evaluation, so then you know how well, whether you should stop and that's good enough, or let's say if its accuracy of the classification is the best you can get is like 80%. So when people ask you to classify, or the machine ask the machine, someone asks machine to classify, machine can say, yeah, I think it's this class, but generally this class of object, the accuracy is only 80%. So then the person can kind of make an informed decision on what to act, how to act on it. And also in terms of choosing the whether there's a better way or approach or model or method to kind of to get a better accuracy and so on. So the task, the learning task, can be kind of subdivided, okay, into different kind of classes or tasks. Things like categorical, like classifications. Okay, so classifications is what we call the categorical, is to prediction the item or to place them in certain class and so on, and you can maybe try to infer further property once it's associated with this class, and then maybe that same class you have a bigger sample, you know the property well, and so on and so forth. The other use of machine learning is, of course, forecasting things like parameters, things like continuous value parameters. So that's the territory of things like regressions, and that's where you want to know a certain value once you, let's say you have things like abscisca. So imagine like you have a function y or x or two quantity that related to each other somehow, but you only have one quantity that you measure. Let's say you measure temperature today, but somehow you think maybe you can predict whether today is going to rain or not with temperature. Then if you have a good model, maybe you can, but maybe you need extra information, right? Like humidity and so on, pressure and stuff like that. Okay, another thing is like characterization, thing to do with testing hypothesis or checking hypothesis, things like what we saw like yesterday, for example, like Gaussian mixture and stuff like that. This could be used to also characterize a sample. Imagine like what we look at the color of galaxies, right? So you can characterize this kind of population or statistical samples of galaxies and things like that. And then, of course, we talked about clustering yesterday in terms of recognizing the pattern, partitioning of the data into different clusters. Okay, but as you know, the clustering fall into the unsupervised machine learning, so you don't need those labels to begin with. So just try to see where they are in terms of distance from one another, and whether there's any emerging pattern from that. Okay, so now we kind of go into the classification task. So what is exactly, well, it's simple, right? Classification, classify. So you want to classify something. In this case, you have a set of classes, so it need not be binary, 1 or 2. And you have something like instance, in this case, data, right? Or example. When we say instance, it could mean the data that you use for training set, as well as the instance that you want to use your model in the future to predict, right? In this case, this could be a targeting area for business, for example, whether these if they fall into the green category, maybe they are good for certain advertisement of certain products, right? So this can be anything, and there's this kind of line that people maybe try to draw. Maybe these data are based on whether how many times they call them, and they accept the product, they go on and purchase the product and things like that. Let's say it's a tele marketing that people call you up and say, would you be interested in this product, and so on, right? So in this case, you can see that perhaps there's a good slide that could separate that, although there's a bit of a outline there that you have to address. So in this case, so once an instance come up, let's say you have the information, maybe your bank sell your credit card information with your phone number, and the information, your instance come up with your education degree, with your age, and then and the business or the telemarketing might kind of like, okay, we have like 100 people, but maybe we can make a phone call like 20 people a day. So who would be best or have more likely chance to purchase the product from us? So then this is what we're trying to say. Then you put in some kind of like classification, and that give you whether, yeah, it's worth exploring or not, right? In that example. So so the given is the set of classes and the data or the instances. So what we're trying to achieve from this classification class is to generate a model, okay, or method to kind of to say how you can how can you divide these two, or how to achieve the goal that you want to do, right? In this case, if you look at the data, okay, fine, it's the like whose separation there. Let's draw the line, and anyone come up to the left of it, I will, you know, call and try to make a sale. And then if it's end up on the right, I probably not going to bother, right? So that's kind of how this works. So so that what is given and what's what you want to get from it. So with the instance that can describe with the set of features, right? So one instance, for example, if we go back to the last example, so that the features or attribute is your age, right? And your education level, right? Instance in this case could be described or ID by your name or your whatever passport number or your ID number, okay? You have features, attribute, and then their value, right? So age and what the number of the age, that's the value, and so on. So sometimes we call this class a label, okay? So when we have the label instance, so that's what you can use as a training set and also test set, right? In order to evaluate how well your algorithm is doing. So again, with the so we will start to explore the first crucial component of this, of course, the data. With the large data set, there's even more motivation to kind of employ the machine learnings, because there's so much data, there's so little time, or you know, someone to be looking at in different parameters and so on. Even giving the classification of variable stars here could be quite complicated. So that would be a good idea, for example, to kind of like using machine learning and maybe even can discover a certain relationship or property that you don't even realize before. Okay, so with large data set, people tend to like to apply machine learning to discover if there's any hidden information there. But of course, if the data set is quite small, it's probably a bit overkill. And it's probably not going to give you something very meaningful anyway. So things like big data set, you can see a lot of image processing. Needless to say, everyone now have always with a camera, right, with their phone. So imagine those informations. You have a geolocation tag, you have tag your friend or facial recognition and stuff like that are flying all around in the social media and so on, and advertisement and stuff like that. So this is a very large data set indeed, and even that is a bit a kind of a generic in a sense that is being used by various platforms. There could be a more kind of strict use of the image processing like CCTV cameras and so on, or in astronomies or in medicals. Okay, so these are all good example of how it's being used. Things like also spam email detection. If I ask you how many spam you get a day, I could tell you that if you don't have spam detection, you probably get way more than that. And so that's actually try to put things at bay a little bit. And sometimes you want things like text mining. People would maybe want to learn about sentimental value. People, let's say government, certain government want to know what people are talking about them, whether they are happy or not happy, or whether they like certain policy change. So sometimes there's this sentimental value or the text mining on the social media, for example, that you can make certain sense of. These most of the time have to be, of course, combined with other things like natural language processing, things like that. So you might have heard of that. There's also DNA data. There's a huge load of that. A very good example and very kind of contemporary would be the COVID-19, that you can see. As you would know, when people synthesize DNA, the information is huge, and most often to kind of looking for certain features in order to edit certain genome, for example, certain trait, then you may need things like machine learning to help you out. And then back to closer to our main topic here is in terms of astronomy. There's a huge load of deal like things like high energy particle physics, things like CERN collider, creating many of those events. At certain time, you have, for example, LHC collide proton. Each time you get a lot of these particles that generated that they need to capture all of them, measure their energy, their momentum, and so on, type of particles. So you can imagine those can enter into features and things like attributes, and then you can learn a lot from that. Or even classification, you can use it to pick only the event that you're interested in, the particle you're interested in, and then discard the rest. Of course, the data will be kept in the central repository. It's just for your own purpose. Things like wearable stars. So on the right hand side here, I put some example from the paper in 2019 from the CRTS, so the Catalina Real-Time Transient Survey. So you can see there classification of 11 types of stellar wearable stars. The number in the bracket down there is the number of stars in each classes. Okay, so you can see that there's also this hierarchical relationship to them as well. So that kind of give you a bit more sort of like physical insight, or maybe you use physical insight to help you with a more accurate classifications. And the lower panel there, that is a kind of confusion matrix. We'll come to that in a bit. In order for you to assess, you have a true label on the y-axis and predicted label. So how accurate it is for you to kind of predict those class of objects and so on, right? So you can see this is kind of like, you want it to be like a diagonal matrix as much as possible. So staying close to 1 in the diagonal, and then anywhere else want to stay close to 0, because that means you are the algorithm is misidentifying or misclassifying the objects. Okay, and then things like galaxy surveys. There are so many of those these days. People are hunting for things like dark energy. You see that at the turn of millennium, there's this big problem that we think we find this X-ray expansion that would need something like dark energy, but then physics, underlying physics theory cannot give you a satisfactory answer, and so there are more and more of the surveys being performed. Many of those surveys is 2D surveys. For example, you take a photometric measurements in different filters at different position of the skies, but most often they would need a 3D information. So that's kind of you save in terms of time. You don't need to do a 3D spectroscopic survey, but then you use the 2D information to kind of infer the distance from us, right? The colors and so on, and the type of the spectral energy distribution, or the SED. I think there'll be a bit of that in the hands-on session on Thursday. Kind of similar things to kind of predict the that. So that is a classification, but rather a classification into discrete class. But rather you can also classification things into continuous number as well. So you will see that happening, and things like in the time domain astronomy. So with the time domain, so Katarina is probably a similar thing because it's real time. You heard of gravitational wave and so on. So that's kind of the survey that now going into the mode where you need a wide field. So you have a huge number of pixels mosaicing, and then with the larger aperture, so it means that you can do a very quick observation survey of skies, and you can perhaps repeat the skies once every weeks or once every few nights and things like that. So things like LSST that is coming along will be also kind of fit into that category, and then depend on the object that you would be interested in, things like blazar, wearable star you saw already, and then you could have radio pulsar as well. People could be interested in optical counterpart of radio pulsars, and so would be searching or try to see if they can get the machine learning on optical variability and whether they can learn anything from that. The other area is astroparticle. As mentioned earlier, that was the high energy particle physics. But then with the astroparticle, the thing is quite similar. Usually you don't kind of expose the camera. The detector is always on, so there's always something happen in the background, and most often those events, or maybe can be background. People, it's just too much. You cannot keep them all the time, otherwise this won't be enough. So usually there might be some kind of machine learning algorithm on the go. So to kind of whether this is the background noise, or is it one of those like dark hot pixels, or whether it is, for example, people could be interested in gamma ray, but it turned out that was cosmic ray. So these could be things that can be used to classify those events. Okay, so apart from those big data set, there's also things to consider, things like complexity of the data set. As you can imagine, with the high cadence or the time domain astronomy, you have the conditions, different night could be quite different, and so on. So that could, you know, make it very hard for you to try to have one pipeline, let's say, that can fit and take care of those conditions. Okay, and then many instances or many examples, that's just the case of just a big sample of data. You can have one instance, or in this case could be one data point, but with multiple features, many of the features. And you can have dependency of different features altogether. So you have correlation, right? So sometimes you think you see something that could be correlated to how you would classify this object, or to see how that give rise to certain property. But as it turned out, it is causing by the other features because of this pass-through correlation, and itself, or at least the first parameter, might not be the, you know, the direct one, for example. So this is also, you know, introduce this complexity into how you interpret the data. Okay, so now with the so let's say you have the data, you start on with the data processing. Of course, you have to do something like instance selection or data selection. If there's any repeating duplicate, you have to remove them. If there's some incomplete, let's say some of the field of your instance, some of the features is missing, you have to come up with how are you going to deal with that. Some or most of the machine learning algorithm doesn't handle the missing data, so you have to do that. So this is kind of like pre-processing of the data. Okay, some people use various different techniques. You could be doing things like interpolation and things like that, right, to fill in the blank, or set some value which is very extreme, and so on, things like that. Some of the features might need some kind of transformation, okay, some kind of scaling. So when you pick the feature, you don't just feed them inside straight away. This type of problem particularly also apply to like thing like yesterday with clustering, when you look at distance. So example, some features like age, right, of the people, it could be quite a wide range, right? People can have a very different age, whereas when you try to measure, or when you use feature of certain thing, it could be just binary, right, 0 and 1. So you could imagine the dynamic range of these two different features could be quite different. And so most often the one with the bigger dynamic range tend to dominate the whole process of modeling. So most often you might need to kind of transform or kind of mapping or scaling those parameters into matching things like from the scale to 0 and 1. So this is also quite important. Okay, so benefit of doing the feature selection is that, of course, the main goal is to have a better classification. You can select things that is noisy, and you can, you know, discard them. You could do things that give you a more cost-effective classifier, thing that, you know, could run faster in order to get the classification and stuff like that. Imagine, I mean, if you think the speed is not important, imagine those automated self-drive car and things like that that need to decide as quick as possible that what is going on and stuff like that. So that is very important. in that case, and things like identification of relevant features for given problem, right? So for different application, different problem, it could be kind of very important in different area. It doesn't mean this same feature would be hold the importance. So this is in the area where you need things like a domain expertise. Okay, so usually when people talk about the data science, it's not all just computer science or statistics or math, but you need to combine with the domain expertise, and this is where the domain expertise will come in. So the way people or the way you could do the feature selections in various ways, you can do the filter approach or wrapper approach. Imagine, for example, with filter approach, you have all the features, you kind of select all the criteria, and you kind of run machine learning. You could do a subsetting of those and see how well in each of the learning set is doing, and then by doing so, you just maybe discarding some of those features that you feel is not actually contributing much and could introduce further degeneracy and stuff like that. The other method is wrapper approach. So the way wrapper approach, don't worry, we have some example later on. So for the wrapper approach, there will be selection of the features, but you can see that it's kind of going back and forward, backward and forward in terms of evaluation, and again, so kind of like subsetting the or selecting subset of the features, and finally you arrive at these optimal features that give you the better algorithm. Okay, so this is kind of the example of the filter approach. These can be used regardless of whatever classification model you use. So what we care here is the relevancy of the of certain features. Okay, some features could be completely irrelevant and you don't even need it. So example is things like a feature you can make quantity thing like feature class entropy that could measuring things like uncertainty and things like that about those different classes that you feel that it could be used. In this case, for example, let's say if you were to use feature 1, 2, 3, 4 in this case, so you can see here you have feature 1, 2, 3, and 4. On the left hand side, you have for example, something that never give you kind of like you have alternate and you always get, for example, F3. If you can see F3, when F3 turn up 1, you always get class of 1, right? So that's something that telling you, okay, this is probably quite a heavy kind of contribution there. Whereas like F1, if you look at F1, F2, F3, and F4, most of the time they kind of like half and half, so 50-50. So it's probably not going to tell you much about it, that whether it will contribute to having a class of 1 or 0. Okay, so that's kind of a filter approach. The wrapper approach is a kind of sequential backward elimination. So you start off from the total set of the features, and you kind of train it, okay, and then one by one, maybe you consider the weight. Okay, in this case, for example, you have feature F1, 2, and 3, and 4. You go on, maybe you do things like random forest and things like that, and you get the weight of different groups of different subsets of the parameters, or it could be accuracy, for example. So in this case, you can see straight away that things like combination that give you a very low, then you probably can safely discard them. So in this case, you probably think that the F1, F3, and F4 is probably the best, so you keep those. And you can then do it further, combining. You have a different combination between F1, F3, and F4, and you can test that further, right? And then you say, okay, all you probably want to keep here is F3 and F4. F1 perhaps doesn't contribute too much to this. Okay, and that's how you finally would arrive at rule kind of like getting rid of some of the features that you probably not going to earn much from keeping them anyway. Okay, so now we look a bit of the classification task. So with the classification task, you start from instance, and then you going through modeler or algorithm, and you try to get the instance. This is example of things like decision tree. As the name suggests, you have this kind of tree-like structure. You start from the root node. So each one of those, for example, here, this is what we call node. So when you come to the node, you have to kind of decide on the value. In this case, maybe yes or no, or it need not be binary. It could be 3 or 4 ways, for example. And then you go down kind of decision making to branch. Okay, so these would be a branch. So you go down a different branch based on whatever the value of the attribute that you're interested in. So this is a node. Okay, so where you test certain attribute, and then when you have the value is what determines which path or which branch you go into, and then you can keep going, and then you can encounter another node. Okay, and then you test the value of attribute of those nodes, and then you pick another branch, which branch to go down to, and finally when you end up at the end, so that's where you get the class output. These sometimes called leaf. Okay, and the top, the highest hierarchy, that is the root. So as you can imagine, you're going from the root, and then you keep going, and then depend on which branch you go to, you end up on something that is could be quite different properties and things like that. Okay, hang on. Okay. So, right. So basically, once you reach the leaf instance, that is what the class or the output that you desire. Okay, so you can things like decision tree is quite effective. Okay, it's easy in this case to demonstrate. Okay, how the machine would make decisions. Right, but the main thing here is you probably look at this and making a mistake of thinking, okay, but these are just conditional, right? So can I code it? So that's the difference, right? If you have to program this condition, then it's not machine learning. So these would be relationship that the machine or the computer would discover out of your training data. Okay, so once you get the model, let's say, so what you want to do with that? You want to use it for classification. Okay, so when you have new instance, you feed that into classifier, which of course take into account the model, right? So once you put in the model, in the case of decision tree, it could be testing those attribute values and so on, and go down the node, and then where it end up with on the leaf, for example. So then you get a class out at the end. Okay, or you can feed in a number of new instances at once. Okay, it doesn't have to be just one. Okay, when you kind of doing a training, usually when you construct a model, you tend to split your data into the training set, okay, and the test set. So usually things could be like 90 or 10%. We'll discuss about that in a bit later. So it's important to have training set and test set, okay, because we mentioned things like overfitting. Okay, if you do overfitting, it might give you excellent accuracy on a training set, but when it comes to test set, it could be really bad. So usually, yeah, it's very important to kind of have this training set and test set in order to assess it. But be careful though, not to have this type of contamination that sometimes the training and test set can be overlap. So it means that when you construct a model, it is kind of somehow dependent, okay, on the test set already. So the test set information is kind of somehow fold in. So that is kind of like a unfair estimation or evaluation of the algorithm or the model that you have. Usually with the classification task, so usually once you hit the classes, okay, we tend to view classes as things that are disjoint or discrete. Okay, it could be a binary thing, 1, 0 or 1, or it could be things that multi-class, if you like. And most of the time, the classification method not always so perfect. Okay, so you can make a lot of mistakes here and there. So so it's important to kind of like have the performance kind of evaluations and know what actually give you. Okay, so now let's come to see the modeler part a little bit, because this is what you're going to be mostly focusing on. Once you have the data or instance ready, you need the modeler to construct whatever the model you're going to be using for classification, right? The classifier most often will be the same algorithm with the modeler, right? But the modeler is more of a training process. So usually the modeler is some kind of mathematical algorithm approach to kind of generalize the instance that you feed into it in order to make prediction, and in order to, of course, to judge whether it's making a good, approach. Things like you can do things like minimize cost function, maximum likelihood, so those type of thing, right? So with that, you can try to see whether you are quite close to the optimal solutions, or you have to keep going. And so, or which way you should go, right? Most often, like, let's say, if you imagine like decision tree, you can choose to go left or right, or split the branch or not. Then you have to pick whether it's better to kind of split the branch and keep going, or should stop here, or go in the different route, for example. So that is also quite important. You might have heard things like also gradient descent and things like that. So that's kind of a similar thing, right? If you imagine the optimum result as being the lowest kind of like cost function, so usually you want to approach to those optimal value, hopefully global one, not local minima, as far as possible. So instead of, let's say, looking in various different way where you should go, like imagine you're going downhill, you want to go down the hill as fast as possible. So instead of like you explore 1 meter this way, 1 meter this way, 1 meter the other way, and see which way give you steeper slope, right? You can go down as fast as quickly as possible. This is kind of thing where a lot of algorithm is doing in there, for example. Okay, so those are again a kind of algorithm where you can optimize things to make things run faster, handle more data, handle more features, and so on. Okay, so the type or the modelers here, or algorithm, there are many of them. Okay, there are many of them. Some of these will be covered during the hands-on. Okay, things like logistic regression, naive Bayes classifier. Some of the name, the name of these could give you certain idea or feeling as to what things, what algorithm will be using. And a thing like support vector machine, quite often you see this as well. It's decision tree. I said that already. We will look at them in detail in the next section as well. There's a random forest, there's kernel method, genetic algorithm, neural network. We'll be looking at that too. We wouldn't be able, unfortunately, we wouldn't be able to look in detail at all these. Otherwise, it would be a bit like one of those, like a touring site where you just step out of the van for like 5 minutes and then everyone jump back in and then just go. So we will look at some of them to get kind of feelings, or get the idea of how it's actually used and the basic behind it. Okay, so again, so right, so once you get, let's say, classification, most often you want to kind of be able to gain physical insight into it. So you want to be able to explain why it's doing, things that it's doing. So in this case, tool like decision tree tend to kind of have a bit of advantage in order to kind of like having us simplify the idea here that we talked about earlier, like how the computer would decide when it's arrived to certain attribute. And of course, now we see this lay out to us, but computers have to also decide out of, or let's say if you look at these, there's 1, 2 features here. So, but the computer have to decide which of these is more of a root, right? So you have something that are more fundamental that form the root node rather than the branch node. So that's also what the machine needs to figure out. In this case, it's a bit simple because you have only the 2 example here. And so when you do that, so example with all those different algorithm, you can see that if you were to represent picking, let's say, 2 classes of objects here, where you can see the blue and the red stuff, right? And using different things to split or classify things, you can see representation here when you go for things like decision tree, how the region could be divided. If you use things like logistic regression, you use things like SVMs. You can see SVM can better deal with non-linear, for example, kind of area, whereas things like logistic regression tend to be handling with the linear area. And if you were to use things like neural network or random forest, you can see the area where it's kind of like try to pick out the classification criteria there. So if you were to kind of, and for example, when you have two classes, this is here, so simple enough, right? With decision tree, it could be just 2 lines. But when you have 3 classes, things tend to get a bit more interesting, right? You can see the decision tree now become more complicated. Neural network seem to be doing quite well. The SVM again give you something that look a bit like, kind of like circular area and things like that. And that, of course, based on, actually, I have to stress on the kernel you use in this case, it was a Gaussian kernel. Random forest, as you can see, it's become a bit also more complicated. Not that far away from the decision tree, but you can see it can handle more kind of almost like overfitting like, okay, but whether that's overfitting or not, that's another thing. So it's just another example. If you start off with 2 sample where you can have like this connected region, right, of the blue, upper and above, and this would be what you would arrive at the model, or kind of approximation of the model to show you there. Okay, again with various other different example. There's also example of overfitting here. So as you can see, when you talk about overfitting, you tend to kind of like go after those tiny fine-tuning features that finally might not give you a more accurate result with the real data, right, or with the testing data. It just happen to be noisy training data set, that's all. Okay, so so just to kind of sum it up, all this, so most often data scientists or someone want to use this will kind of like have to check through various things. So normally you don't just land on decision trees and then you just stick with it and you're happy and you're not doing anything else. Most often people tend to kind of like, go for the one they are familiar with, or the way that the features they have is more suitable for them. Even that, sometimes they are being compared, which one give you a better result, or sometimes people might, not able to choose which algorithm or which modeler is better. They go for things like ensemble modeling or ensemble learning. So basically, you can have different modeler or different of those algorithms, and you do basically combine of all of them, right? Each one could have a different way, maybe based on accuracy of those different results, and then combine these modeler all together. In this case, you can have this classifier 1, 2, and 3. You can combine them, and final answer is something in between. And that's, of course, with the hope that you get something of a very good accuracy. Okay. Let's see how we do the time. Okay, so right, we have about half an hour. Okay, so next, just want to kind of quickly go through some example thing like decision tree. We talked about that already. Finally, you land, at the leaf as the classes. You have the node as one of those features that you have to check the attribute value, for example, and then once you satisfy whatever the branch, then you go down that branch up until the point where you reach the end, which is the leaf, and that's why you get to decide what class it is, right? So example of things like these, again, things like, okay, should we play golf or not, based on things like outlook, whether it's sunny, rainy, overcast, temperature, humidity, windy, and stuff like that, right? So as you would imagine how people would make a decision on this, could be instance that in the past, right, people, or maybe your friend could be calling, ask you out, okay, shall we go play golf and things like that, right? Or you ask your friend, and whether your friend, most likely that he or she will go with you, right? Things like that. So yeah, you could imagine. So these will be a kind of like the features that you would want, and finally the answer come out to, okay, yes or no, right? Most like, is it likely that we will get to play golf today? Things like that. Okay, so with the decision tree, again, similar example like before, you can see something like this. So these circle in red, that is the attribute or the features, right, forming the node where we can make a decision. The one that label there in green, so those are the attribute value, right? So in this case, when you consider outlook, whether it's sunny, overcast, or rainy, then that's where you kind of decide which branch to go down, right? Once you go down the branch, you see the next node, and you test those value again, up all the way until you reach to the leaf. So that's the end, right? So then you get the answer or the class, whether yes or no, and stuff like that. There's this artificial neural network. Artificial, as you know, is not a neural network, because you try to kind of mimic what you see, this kind of like a neural cell or the brain cell neural connections network of human or animal, and try to kind of use it to make certain prediction or classification or make decision, basically, right? So imagine you are trying to make decision on certain thing. All those things like decision tree is actually happening in your brain, right? Connecting various different brain cell and different node, you know, as you know, if you like, to decide on, you know, certain condition, and then you end up with the answer, right? So these are kind of the thing that, for example, you have this input signal in, and you have this kind of black box things, right, which already wire in certain way with these different weight. Okay, so different people could have a different decision, right, because their weighting or whatever or how their network connect together could be quite different. So even on the same thing, based on experience, people would say this is one thing, and the other person would say something else. So that's kind of analogy to that. And finally, you get the output out to whatever you want, right? It could be classification of pictures. Is this dog? Is this horse? Is this cat? Things like that, right? And the way that it used mathematics to kind of mimic the neural cell is that this what we call the activation function. Okay, so you have things like activation function to kind of a way to kind of, okay, because you saw earlier like decision tree, right? So this is kind of the same to go down this part, or down once you reach this network, which other network cell or network node to go through next will be this kind of like activation function, okay, which take into the weight of different parameters and so on, right? And that's kind of finally get you to the final answer based on your input. Okay, so now let's talk a bit about the overfitting. We talked kind of in passing about this quite a lot. So what is overfitting? When you try to get your training data set to be so accurate, sometimes you can go into this overfitting. It might appear to be giving you quite good performance or accuracy at first, okay? But since this, you try to kind of fitting the like outlier or high uncertainty data point, so it means it's not representative, right, of the real data set. So it means that your model is, you know, overfitting. It means you cannot really get a really representative model. So beware of that. You know, trying to get accuracy so high, take into account every kind of noisy data. That could be what you might be running into. So the way to avoid overfitting, things like separate training and testing data set, as we saw earlier. You can do things like cross validation. You can have some, you can keep your model as simple as possible. Things like the number of free parameters or whatever that you model, cluster, and try to keep them as, you know, if you have the two, you have a let's say base number where you have a cluster numbers that the accuracy is not that far off, okay? But then one cluster require a high number of cluster of k, so that is a good indication that you go into overfitting into this, you know, tiny cluster in order to kind of like make them accommodate each other. So that's kind of just make things simple, right? So this is what the pictorial representative of overfitting, like similar to the problem we saw earlier, right, with the education age, for example. You can see that there was a bit of outlier there, and if you were to kind of like make sure you get all this data, right, so you probably come up with the model or this line here, try to go and then try to also enclose this region, and then kind of come over this green point here, something that looks something similar like this. Whereas in the real data, right, because these are training data, it could be some noise. Test data could look something like this. So with this, it will seem fine. But when you put this overfitting model into this, you can see that it will potentially perform worse than the first one. Okay, so that's what we mean by overfitting. So now we will spend the last part of this on the evaluation of the classifiers, models, or modelers. Okay, so usually in order to evaluate its performance or its accuracy, we have a various way. Okay, first, of course, with what we said earlier, with overfitting, you should have this training set and test set. Okay, so but for example, you take some fraction of your data to become training set, D-train in this case, and then you have a testing set. Of course, D-train is the one that's used for to get your classifier, to get your modeler to learn the model and construct the model, and then the testing is exactly as the name says. So you get the idea as to how well it perform, because since the model is trained on those kind of subset of the same data set, so it's very important in terms of overfitting as well, as we saw earlier. So yeah, so this is very important. Okay, so because of this, it means that usually in order to do things like machine learning classifications, you have to have a big set of data. Another technique that people use a lot is what we call the info cross-validation. We'll see that in a little bit, what it means. Okay, so basically what you can do is you can subset your data into n kind of equal size, right? You can split them into 10, let's say, for example, 10 subsamples, and in turn you can do kind of training on the n-1, right? So you just, for example, you test on you train on 90% of these, and then you test on the rest, 10%, and then again you kind of take turn, right? So you discard a different set, different 10%, for example, and then you can use this to kind of help you, even though the data could be limited, you cannot generate new data. This would be one way to kind of like get some more inside information based on how you kind of select your data. Or you could, I mean, potentially you should do things like randomly selected, right? You shouldn't split them by sorting the value, or you shouldn't do like sorting the value, for example, in some numbers or some features or attribute value. You have a range of something to something, and then you happen to sort them, for example. That is not a good way, right, to do enfolding. So you have to be very careful. So things like 10-fold and 5-fold cross-validation is quite common. Okay, so that usually people do this quite a lot. So again, like I said, this is quite useful, especially when your data set is not very big to begin with. Okay, and then things like leave one out cross-validation. Okay, so a kind of a normal, like testing and training set like we saw earlier. Okay, so sometimes people then have this validation set as well. Apart from training and test set, you still have a validation set. Okay, validation set is used for things like estimating the parameter in the learning algorithm. You will see that, especially during the hands-on, you will see that many of these algorithms, when you use it, there are numbers of parameters or options that you have to kind of choose or decide on, and these can sometimes, most of the time, dictate your final outcome. So it's also quite important to have this validation set to check all those out as well. Okay, so this is what we call the kind of like cross-validation of 10-fold. Okay, so you start off from like a training set, which is the 9 or 10, right, of those original data set. You then go through machine learning classifier and so on, and then when you have those model or classifier, you use a 10 of those data set, right, and check those, right, with the model that you have, do some performance calculations, and then you do that, basically repeat that 10 times, right, because you have each time you can describe 1 out of 10. So example is something like this. You have a pictorial kind of representation of info cross-validation. In this case, it's split into n sample, and each time you use those sub sample, right, in each iteration. So iteration will end up equal to n. Okay, right. So now, once you have the classification, you have a testing set. So now, how do we evaluate how all the algorithm and so on perform? Okay, so most often, right, when you classify something, you would think, okay, I will focus on accuracy, which is not bad. Of course, you want to classify, you want to know how often you are correct, right? So that's a good thing, right? Or you think about, if you focus on error, the error is 1 minus accuracy, is the same thing, two sides of the same coin. But as you will see that accuracy is doesn't give you the whole picture of what is going on. Okay, so there will be other parameters that are defined using what we call the parameters in the confusion matrix. We'll see that in a bit. So example of the case where accuracy might not be just suitable as the one to decide, right? Things like algorithm that you would use is things like, you know, text mining. For example, you could be interested in things like one of those minor kind of like minority class and stuff like that, minority report and things like that, right? So so that, yeah, kind of thing. The same thing with the classifications. Most often you might not, you know, interested in the accuracy, but rather to pick up all those, you know, anomaly, which is very tiny. And so it's very important to pick many of those up. Sometimes that's why we need other metrics like, you know, sensitivities, things like we'll see about that. Yeah. So usually we tend to call the class that we interest a positive class, okay, and the rest as the negative class. So this is a convenient definition if you consider a binary classification, right? So like 0 and 1, is it a dog or is not a dog? But if you have a multi-class, multi-classification, this way you still can do things like a positive class, negative class inside, but it's a bit more complicated, like we saw earlier with the variable stars. So you can have like a cross match between different class, because when you talk about negative class, so let's say you so example is just before, so instead of saying this is dog or not dog, it could be turned into, is this a dog, a cat, or chicken, right? So you can see that there are 3 classes. So in the case where you validate chicken being chicken, so that's a positive class that is what we call true positive, right? But if it's a picture of chicken, but you classify as being a cat, right? So if you're interested in looking for chicken, you could consider that as being a negative class, right? So anything else that is not chicken, you can consider them as negative class. So that, you know, give you a bit more complicated confusion matrix, okay? But if it's binary, it's pretty straightforward. Either it is or it isn't. Okay, so more often people will be looking at this confusion matrix, right? So once you classify, here you have what we call the predicted label. Okay, so that's what your classifier give you, and you have a known label. So that's basically your input data, your testing set, your validation set, whatever. So the case where you want to have a lot is, of course, this, the one that predicted to be positive and it turned out to be positive. Okay, so these will be called true positive, and you will see normally we'll be using like TP as the abbreviation, and you have the other end of this would be a false positive, so FP here, right? So your classifier said it is, but in fact it isn't, right? So this is false positive and true positive. And then there will be a class where your classifier said it is not what you want, right? It's a negative, okay, in this column. But if it's turned out to be a really negative, okay, so it will be called true negative. So this is something that you wouldn't want, okay, in the first place anyway. So these two in the diagonal here, this is what you want to be high as possible. right? And then you have things like false negative. Okay, so as you can imagine, you have a kind of a negative word twice, right? It's a minus, and minus is a plus. So in fact, the false negative mean it is what you want, but you misclassify it and you overlook it, right? So with the chicken, dog, and cat example, if you're looking for chicken and if it's classified as being a cat and it turned out to be false negative, means it's really a chicken, but it was the machine, the classifier said it is a cat. So that is something you probably missed, right? So you couldn't be missed out. Okay, so you can imagine with these parameters what you can learn about various metrics. So first of all, sometimes people talk, say this about precision. Okay, precision, or sometimes called just precision. Yeah, it's not the accuracy, because accuracy you take the other part as well. We'll see in the next part. So precision, okay, so not to be confused with accuracy. That's a good example that I was about to actually forgot about that. So precision will be focused on the positive class, okay. So as you can see here, the precision would be the ratio between true positive over the true positive plus false positive, right? So basically we focus on because when you do the real classification, you don't know whether it's true or false. So you would think that, okay, whatever the classifier tell you that it is, right? So the positive class, you want it to be as correct as possible, right? So the TP, so this will be TP over TP plus FP, false positive. So it means that if you have low false positive, this P precision should be quite high, right? Ideal case is to have 0 false positive and you have 1. Okay, and now we have things like recall. Recall is sometimes called sensitivity. So recall then would be again true positive divided by true positive but plus false negative, right? If we go back to see this class again, known label, that is a positive. So these are the real deal, right? But you misclassify as negative. Okay, so if the false negative is high, it means that your recall or your sensitivity is low, right? Your sensitivity is low means you don't pick the thing that's supposed to be chicken. The machine classify as dog or cat, right? So it means you pick up, you're not sensitive at picking up chicken, right? So this is a kind of a very important idea, because why? As you will see that when you judge the algorithm, it turns out that just precision is not good enough. You also have to consider recall, right? You can imagine the case where you can have precision very high, right? So for example, you pick the position, the positive class. Let's say you have 100 objects, and if your classifier is not sensitive, it could pick only 10, right? In the positive case. So this TP could be true positive could be 9 out of 10. So it might give you a false sense that it's a good one. But in fact, there's again another, I don't know, maybe 50 that's supposed to be positive that have been classified as negative, and it turned out to be false negative. So most often you will have to kind of optimize these two at the same time. Okay, and there's another parameter that kind of defined in terms of combination of these two. Okay, and sometimes you might also heard of other parameters as well, things like specificity. Okay, specificity, as you can see there, will be defined as a true negative over true negative plus false positive. So that's basically a kind of like a sensitivity of the negative class, right? If you think about in that sense. But for accuracy, okay, I kind of earlier I said accuracy and precision. You see how it can get confused with the word. So accuracy have a very specific meaning. You can see here. So when we talk about precision, you only focus on the accuracy of the positive class, right? But when you talk about accuracy, you care all about whether it's positive or negative. So in this sense, you have both true positive and true negative on the top here, and you divide it through by everything, right? So everything, so that gives you accuracy of all the class, not just the true, not just the positive class only, right? Another parameters that people could also define things like correlation efficiency. in order to kind of measure how well the identifier thing work. Okay, so it can be given in this kind of formula, and so yeah, as you would have guessed, correlation usually going from -1 to 1, right? So this will give you like a correlation. If it's all random, it seems like random. There's no good result. You get something like 0. But if you get to something like a very good result, ideal case, the correlation, as you imagine, correlation coefficient would be 1, right? In the case where you have very low false positive, right, and very low false negative, right? So basically, this term here will go something very low, right? And the same thing here at the bottom, you will get something that you have a term where you have TP multiplied by TN square. Okay, so then you get something like 1. Okay.
Utane, it's 15 minutes.
Yeah. Okay. I have another like 10 slides, so hopefully that should be all right. Okay. So another way to use is, in fact, use what we define already, but to kind of have a more way to kind of like choose the optimum point. We use this, what the so-called F1 score, which will be, as you will see, we can be combination of precision and recall. And you use things like ROC, receive operating characteristic curve. And then from that, you can estimate the AUC, area under the curve. We'll see that. Okay, what we mean by that. Other metrics apart from those, of course, for some people who want to have some physical insight, might want some kind of explainability, right? Why classifier give you in this way? They want to, you know, learn the pattern and things like that. And even more so things like various things like cost of the feature values and calculation time and things like that, if you want to kind of evaluate the performance of your classifier. Okay, now there's a F1 value, F1 score here, which defined as being 2PR divided by P plus R, right? Or you can kind of rewritten in the lower expression. So what this does is that, as we saw earlier, we want to optimize such a way that precision is high and recall is high, right? But I mean, how you can do that at the same time? Sometimes as precision get higher, recall can become lower. Like in the example we just give, right? You can if the algorithm is not very sensitive, you pick a very low number, and those turn out to mostly right, but then there's still a real object in your sample, but you don't pick up. So that will make your recall very low, right? So this is a kind of a number to help you kind of optimize for where it's like a sweet spot, if you like. Okay, and now move on to ROC. With the ROC, the received operating characteristic curve. Usually, this is the plot where we plot the false positive rate on the x-axis, and then you have the true positive rate on the y-axis. Okay, so true positive rate. What we mean by true positive rate is, of course, the true positive divided by true positive plus false negative. Okay, so false negative, that's the true object, right? So this is basically when you pick up the objects, how you pick how many. I mean, what the fraction of the real thing, right? You manage to pick up. Okay, and false positive is the other class that you don't consider, right? So things like when you pick up things like false positive divided by true negative and plus with the false positive. Okay, so usually you plot like this. So you have false positive on the x-axis and true positive rate on the y-axis. Or I can show as this kind of function, but it's still the same plot, right? So in this case, you can start to have a look, right? We want to have a true positive as high as possible, right? It's scale from 0 to 1, and also x-axis false positive rate from 0 to 1, right? So first of all, if we have a diagonal line that going at 45-degree angle, that means, what does it mean, right? So what it means here, you have 50-50, right? So that's just like randomly pick them. So with this line, it means that this line is just running at something like 50-50, right? If you were to integrate the area under the curve here, you will get half of the total things here. So the area under this curve here would be the width multiplied by the height, so you get 1. So you integrate the area here would be a half, right? So that kind of lead on to AUC, area under curve. On the opposite side, okay, like we say earlier, you want to have true positive as high as possible, but as you can see, it will get higher eventually, but at the expense of the false positive rate will become higher too, right? So as you can imagine, if you want to optimize it, you want to push this green line, for example, as close as the upper part as possible, right? So this is what it said here. So moderate is this green, is this red line with the diamond, okay? Random is this one here, and bad is if the line is under here, it's bad. So you have false positive rate growing faster than the true positive rates, and that's not something you want, because then it's worse than a random case, okay? So and then you have a better case, which is the green one, so the rate in the green is better, and then perfect case is this one up here, okay? You might not be able to see, but this is perfect case. Most often it will rise up very fast and then kind of curve here a little bit and then approaching asymptotically to 1, right, at the high false positive rate. Okay, so that's the ideal case. So once you integrate the area under curve, you can see that as you go from this light blue line to what is it, magenta line to red line to green line to dark blue line, you get area under curve to become higher and higher. Okay, so in this case, if you need to decide between these two models, sometimes it's a bit more complicated, right? Because it doesn't just all one above the other. It could be some area where it's higher, but then it go down under the other. So the proper way to do that is to actually using this to estimate the AUC, or the area under the curve, and with the higher AUC, that indicate that your classifier is doing better. Okay, so for example, with this C1 and C2, which is kind of similar to this one, okay, with the C1 and C2, we can see this area where C1 is higher and then come down lower. So you probably cannot just look at that right off and say the algorithm C1 and C2, which one is better, right? So these, by the way, is depending on the same data set. Okay, so then again, yeah, with the area under curve, then that can be decided straight away, right? The closer to 1, that's the ideal case. 0.5, that's just, you know, random. Anything less than 0.5 is basically just worse than random casing. So we're not learning anything from it, basically. So usually how this, you know, would do is something of a sort, something like this, where you let's say you have a different classes, and then you have the matrix kind of like similar to confusion matrix, but rather you kind of have this true positive, false positive, and all this, right? And you kind of draw this curve. I think you will get to do that in the hands-on if you haven't done so already on Thursday. Okay, so from that, of course, you will get those performance in terms of accuracy, precisions, AUC, and all that. But then there's other consideration to take into account, things like what sort of factor, right, to help or affect your performance. Things like, yeah, large amounts of data, features. Features is what we call the higher dimensionality, right? So you know, make things rather complex, and it could, you know, not necessarily more features could be better. More features sometimes is not very important, but just to introduce extra degeneracy, so could make things work, end up making things worse. The features, some features appears very few times in the case of sparse data, missing data. So you can have a number of instances, but certain features are not kind of either non-documented or whatever the let's say the detector didn't register it and just empty value and things like that. So that will also affect how well your classifier perform. If you have a very complex classification, there's no such thing as a free lunch. You will need to have more instance or more data in order to discover all those complex relationships. So there's no way around it. You need more data. Okay.
Utane?
Yes.
5 minutes. Sorry.
Okay. Yep. I will have a summary in a bit. Okay. So So yeah, so uneven and things like that as well. As we haven't even touched on what happens if you have two classes or objects and one class dominate the other, and that could, you know, could tip the classification toward the other side, because more often the model get a chance to classify this class more than the other. So naturally, you would assume that it's more common to have this class, right? But this is the problem of the unbalanced training set. Okay, to summarize and sum it all up on the classification. So let's say when you're facing with classification tasks, what sort of thing you want to do. Let's assume that you have all the good data, you pick all the good data, there's data processing everything that you take into account. You start to have to consider in terms of the features, right? Sometimes it's good to kind of using your background knowledge, your domain expertise to kind of think that, okay, so if you want to classify certain things, there's these features that is a must and you think it's really important, then you make sure that it's in. But most often you don't know because it could be overlooked or something that hasn't been discovered that you want to put in. So features is quite important in that sense. Where is the perfect balance between, okay, let's put something just in case there's something we haven't learned about already, and you know, we could be interesting, and you know, and just put in too many features that is actually ruining the whole thing altogether, or introducing extra degeneration and so on. So yeah, so things like 100 to 1,000 features, that's a bit too much. Of course, that could be dependent on the problem that you're considering, but usually order of tens, that's quite a high number, okay, for what you're trying to do, mostly. Yeah, okay, so sometimes the observable, like some of the features and some label might not be what we say directly observed. It can be kind of a hidden or latent kind of variables that how to say, it's quite objective to kind of define these features. So this is also something to bear in mind. It might be directly observable, but sometimes it's calculatable, and those calculatable features value sometimes is model dependent, so you have to also be careful on that. Okay, and things to consider then, things like classes, right, that you want to pick. Example would be if you want to classify mushroom, whether it's edible or poisonous based on pictures, right? So this will be either edible or non-edible and things, or unknown. Okay, if it's a 3 classes, so you have to choose and decide from the beginning, and sometimes the choice does matter of your final outcome. So again, this is a label examples, the instance, the data. In terms of the training set, okay, you have to know how many you have, and in order to have the test set, the validation set, how would you approach, right? We have this info which good for low number of data, that could be something that you could use. And then finally, the modeler that you want to use, right? What you can choose for algorithm that we talked about earlier already, and sometimes maybe just to put a lot of them in and then have the ensemble one could be quite interesting as well. So people does do that. Okay, so these are kind of like summarizing of what we usually have to face with classification. So yeah, so for that, I'll stop here. Thank you very much.